the final topic which we're going to do today and tomorrow is an algorithm for finding the biggest set, the largest y, which is independent for two matroids at the same time. So the largest set y in I1 intersect I2, where xi1 and xi2 are matroids. Right, and as it turns out, so I'm not sure if we're going to see if we're going to have time to see a lot of applications of this, but you can take my word for it that this type of problem, it has various different applications, and yeah, so this gives some more motivation for studying matroids. Of course, I'm sure that all of you already think matroids are awesome, so you don't need that much more motivation, but this is, this gives a bit more motivation. And in fact, believe it or not, the algorithm that we're going to present can even be used to, for example, prove Koenig's theorem again. Right? We've proved that at least twice already, and this can give a third proof of Koenig's theorem. But today, so tomorrow we're going to give the algorithm. Today we have to prove some technical results that will help us to verify that the algorithm is correct. So in fact, there's really just sort of one, so maybe I'll just say there's really just one sort of technical lemma that we're going to prove. And we're going to use that lemma tomorrow. Okay, so right, so this is, so a lot of this this algorithm has to do with matchings, believe it or not. Okay, so before proving this technical lemma, we're going to need some other results, and I'll state them now, and then if we have time at the end of the lecture today, I'll prove them. But both of these kind of follow in a not too difficult way from Koenig's theorem. So to prove the technical lemma, we will apply the following. Okay, so first, actually, I need a definition. So given a graph G, and a set of vertices, so I'm not sure, maybe I've defined this before, but in any case, it's good to be reminded. So we can define the neighborhood of this graph to be the set of all vertices joined to, the neighborhood of this set S to be the set of all vertices that have an edge going to S. So define so I'm going to, the notation I'll use is n sub g of S, because sometimes it's going to be important to remember which graph G we're talking about. And that's the set of all vertices such that there exists U in S with U, V, and edge. This is the so-called neighborhood of S in the graph G. Right. Okay, so what we're going to need are the following results. So So this is a theorem called Hall's theorem. Actually, I believe in one of the exercise sheets you're asked to prove this, but yeah. So if we have time at the end, I'll prove this. It's an easy application of Koenig's theorem, but so it says that so let G be bipartite. So it's a bipartite graph with bipartition, let's say AB. So we want to say G has a perfect, we want to characterize when G has a perfect matching. So G has a perfect matching. Remember, a perfect matching is a matching that saturates all the vertices. So every vertex is in one edge of the matching. And if and only if, so G is a perfect matching if and only if, well, okay, sorry. So here, the bipartition has the property that the size of A equals the size of B. Okay, so we want to say G has a perfect matching if and only if the neighborhood in G of S is larger than S for every S contained in A. So every set, yeah. So it's not hard to see that this is necessary in order to have a perfect matching, because if you have a set of vertices such that if you look at all of their neighbors, it's smaller than the set, there's no way you could possibly find a matching that hits all of those vertices. But this turns out to be equivalent to having a perfect matching. So kind of a hint. And like I said, maybe we'll actually prove this at the end, but but to prove this, it's not too hard if you apply Koenig's theorem, which says the size of the biggest matching equals the size of the smallest vertex cover. Okay, so we need this theorem, and we also need the following. Or actually, yeah, okay. So we're also going to need this. So let G, so again, be a bipartite graph. With bipartition AB. So yeah, so we're going to need something about when a bipartite graph has a unique perfect matching. So so if G has a unique perfect matching, so PM will just stand for perfect matching, then there's a vertex in A with degree equal to 1. Meaning, so degree, remember, is the number of edges that contains the vertex. So what we're saying is that there's some vertex in A that's only contained in one edge. Okay, so so let's take these two things as a given. And now let me state this technical lemma, which is going to be the main thing that we want to prove today. So first I need another definition. So given a matroid, so I'll call this matroid M. So M is the pair xi, and a set, so an independent set Y, so we're going to define some sort of graph based on Y and based on the matroid. So H and Y be the bipartite graph where, so the vertex set of this graph is X. X is the set where the matroid kind of lives, right? So the vertex set of this graph HMY is x. It's a bipartite graph, so the bipartition is, so on one side you have the set y. On the other side you have everything that's not in y. And now I have to tell you how the edges work. So for y and x, so this is just one side of the, so y is in, like, say the left side of the bipartite graph, x is in the right side. So the edge from y to x is included in the graph if, so, okay, so y, remember y is an independent set, right? So, okay, so the condition for containing this edge is going to be that if I take the set y and I swap out the element x, or sorry, the element y, so I delete y and I add in x, that this maintains independence. So this is an edge if the set where I throw away y and I add in x, if that set is independent. So the graph, this graph sort of encodes, yeah, so you have this set y, and this graph kind of encodes all the ways you can just delete something from y and add something else and get another independent set. Okay? So why do we care about this graph? So here's the technical lemma, which is going to be quite crucial tomorrow. So I want to use this graph to kind of be able to, so I have that y is independent. I want to be able to say that something else is independent. So yeah, so let, again, M be a matroid and y be an independent set. So, and let Z be a subset of X, which at the moment we don't know if it's independent or not, but so let this be, so let this be any subset of X, such that it has the same size as Y. Okay. And I want to be able to say that somehow using this graph, if there's some sort of, if Z has some property, then I can show that Z is also independent. So the statement says that if there is a unique matching in HMY from Y minus Z to Z minus Y, then Z is also independent. Now, what do I mean by matching from here to here? So matching from this set to this set just means matching using only edges from Y minus Z to Z minus Y, which saturates both of the sets. So every vertex here and every vertex here is contained in such an edge. So saturating both sets. So the picture is like, so this is the set Y, this is the set X minus Y, right? This is the, so here we're looking at the graph HMY. Here you've got a set, the set Y minus Z. Y minus Z lives over here because it's a subset of Y. Here you have the set Z minus Y. It lives over here because it doesn't contain any elements of Y. And we know that these have the same size because Y has the same size as Z. And our assumption is that there's some matching which matches every element here to an element there using an edge, but this is the only, so this is the only matching from this set to that set. Okay? So that sort of explains why this proposition might be useful. Because if you think of just the induced subgraph by the subgraph induced by these sets, then what we're saying is that this red matching is the unique perfect matching in that graph. And that allows us to apply this proposition. Any question about the statement of the lemma? I know it's kind of technical. And the proof is even more technical. Okay. Sorry. But it's going to be useful. So, okay. Right, so we go by induction on the size of z minus y. So the base case is actually when this set has size 0, right? And that turns out to be trivial. So when this is 0, that just implies z is equal to y because z and y have the same size. And if this is empty, then they just have to be the same set. And that, because y is independent, we just get z is independent. Right? So that sorts the base case. So now assume that this is at least 1. Okay, and we want to somehow use induction. Okay, so let H prime be the subgraph of this weird bipartite graph HMY induced by y minus z union z minus y. Okay. So in this picture, basically, so this picture up there was the whole graph HMY, and we're just going to zoom in on this, just the vertices, which are in y minus z or z minus y, and we just look at the edges between those sets. So the fact that there's a unique matching from this set to this set is the same as saying that H prime has a unique perfect matching. So H prime, well, this has a unique perfect matching by the assumption in the lemma. Right. So now we can apply this proposition. So this proposition says if you have a bipartite graph with only one perfect matching, then you can find a vertex of degree 1, which is in A or in B or either side of the bipartition you want. So by the proposition, there exists some y in Y with degree 1 in the graph H prime. So let Z be the unique vertex, so the unique, say, Z in Z minus Y, such that yz is an edge of H prime. Okay. So now we're going to, so we're going to do a sort of a trick where we're kind of going to, so we need to apply this inductive hypothesis somewhere, right? So we need to find a set Z prime which is more similar to Y than Z is, and somehow apply the inductive hypothesis. So we define Z prime to be the set where I take the set Z, I remove little z, which is the unique neighbor of Y, and I add in Y. Okay. So in some sense, right, you should think of this set Z prime as being, if you kind of think of how similar it is to Y, it's more similar than Z, because I took away something which wasn't in Y, right, and I added something that's in Y. So if I look at Z prime minus Y, that's going to be exactly equal to Z minus Y minus 1, because because this set is literally, the same as taking Z minus Y, but then you also have to throw away little y because little y is inside of Z prime. So this set is equal to this set, which of course has size smaller than Z minus Y. So therefore we can apply induction to this set as long as we know it satisfies the criteria. So maybe I'll remove this definition. Okay, so right, so I claim that there is a unique perfect or matching in HMY from Y minus Z prime to Z prime minus Y. And if that's true, then we can apply the inductive hypothesis to Z prime. But this is actually not hard to see because if there wasn't, then you'd get another matching from Y minus Z to Z minus Y. Okay, and the reason is because so if there were basically the proof of this is if there were two different such matchings, then we could just add the edge YZ to each of them, and that'll give you two different matchings from Y minus Z to Z minus Y. So if there's two different such matchings, you can add the edge from Y to Z to both of them, and that will give two different matchings from Y minus Z to Z minus Y. Okay, so the point here is, so the picture is like what is Y minus Z prime, right? It's the same thing as Y minus Z, except that it doesn't contain this vertex little y, right? So this bottom part here is Y minus Z prime. This thing is Y minus Z. I know this picture is not so easy to see. this is z prime minus y. This whole set is z minus y. Basically, if I was able to find two different matchings going from here to here, right, then I would just stick in this edge. So I know that there's an edge from y to z, and I would just use that edge to get a matching from to get two different matchings from this whole set to this whole set. Oh, and I should also say that there is actually at least one matching from this set to this set because, well, so the reason is that we know that the edge from y to z must be in the original matching from this set from y minus z to z minus y because that's the only possible edge coming from y. So when I delete this edge, you find at least one matching here, and I'm saying if there were two, then you'd have two in the beginning, and that would contradict the assumption. Okay, so what I'm saying here is that we can apply. So therefore, we can apply induction to z prime because, yeah, it has z prime minus y is smaller than z minus y, and it satisfies all the same conditions. And the inductive hypothesis then implies that z prime is an independent set. Okay. So now we need to do some more work to prove that actually z is an independent set. Okay, actually maybe I can. So now I'm going to erase just the statement of this lemma, but I'll just kind of write our final goal. So is to prove that Z is an independent set using this information that we already know that Z prime is independent. And we're actually not, so we've actually used, the hypothesis of the lemma the only time we're going to use them. So I'll just erase this, and then we're just going to focus on using this to prove that. So we know that Z prime is independent. So if I look at Z prime minus y, which is of course the same as taking Z minus x, or sorry, minus Z, little z. If you just look back to the definition, this is the same thing. So this set is independent, right? So now what I'm going to do is try to find a so we find a set U such that, and we need several different properties. So we want, okay, so first of all, U is going to be an independent set. That's no problem. Z prime minus y, or so this is the same as this. Let me write it as Z minus little z. We want this to be a subset of U. We want some more conditions. So we want that U is contained in y minus y union z, sorry, capital Z. And we want that the size of U is equal to the size of y. Okay, why does this exist is the question. Well, so this exists simply by the third Matroid axiom, right? Because, so basically if you start with the set Z minus Z, so this is independent, and wait a second, I need, so this is a sneaky thing. And if I look at y minus y union little z, this is independent, why is it independent? So this is actually the only time we're really using, or so far at least, the structure of this graph HMY. So this is independent because the edge YZ is an edge of HMY. Right? The edges of this bipartite graph say that, so if YZ is an edge, it means I'm able to remove Y and add Z and maintain independence. So this is an independent set, and this is an independent set, and this one is bigger than that one. So the latter one is larger because it has size Y. This has size Y minus 1 because Z is the same size as Y. So there's some element I can remove from this one and add into that one and maintain independence. So by the third matroid axiom, so there exists some, say, W in Y minus Y union little z, which can be added to Z minus Z to get another set which is independent, and that set is going to be U. So to get the set U. So when I start with this set and I find something here that I can add and stay independent, you're going to get a set U which is independent. It contains Z minus Z. It is contained in this set, and it has the same size as U. Because it started as something one less, I added one element, it got bigger. Okay, remember our final goal is to prove that Z is independent. So suppose that Z is not independent, and we try to get a contradiction, right? And if we can get a contradiction, we'll be done. Okay, so if Z is not independent, then we know that little z cannot be in U. Why? Well, if it was, well, then U would just be Z, right? Because U contains all of Z except for little z. If Z was also in U, U would be Z, Z would be independent, we'd be done, right? Because U is independent. So if I look at where U lives, it actually, so I said before it's a subset of what I've written there, but it's actually a subset of this. If I take Y union Z and throw away both Y and Z. Because because we know it's a subset of what I've written up there, and it doesn't contain Z, so it's a subset of this. So now we do a similar sort of trick as we did to construct U, but we construct another set T. So we find a set T such that, so we want T to contain Y minus Y. Actually, let me write things in the same order as before. So T is independent. T contains Y minus Y. T is contained in Y union Z minus little y and little z. And the size of T is the size of Y, which is, of course, the same as the size of U. I mean, all of these things have the same size. How do you find this? Well, you do the same trick as before. You just start with this set, Y minus Y. You apply the Matroid axiom using the set U. That'll find you an element you can add to this set, and it'll stay a subset of this because U was a subset of this. Okay, so you won't have added something which is not in this set. Okay. Oops. So the proof is done, basically, believe it or not. So what's going to be the contradiction, right? Well, okay, so this is, yeah, so, I mean, T contains this whole set, y minus y, and it has the same size as y. So it's basically, I mean, it's basically this, it's this set plus something else, right? So T has the form, so T is equal to y minus y plus something else, plus some z prime. Because it contains all of this, and it's the same size as y, it has to be of that form, where z prime is not z, because T is contained in this set, so z prime can't be z, because T doesn't contain z. And z prime is somewhere in, it's something in z minus y. Okay. But that's a contradiction because, weirdly enough, so this implies that if I look at the edge, if I look at yz prime, this is an edge of this graph HMY, because it's possible to take the set y, remove little y, and add z prime. But remember, y is supposed to have degree 1, right? So this contradicts the fact that y has degree 1 in the graph H prime, which is the subgraph induced by y minus z and z minus y, right? Because so we found, yeah. So what we found is that, so we knew that y had a neighbor z. We found another neighbor z prime. They're different, so that's a contradiction. Okay, so that's a. It feels like a very strange argument, but yeah, this is going to be useful tomorrow. Let me see if I can give you a quick proof of Hall's theorem. So we didn't actually use this. The reason I stated this is because actually, if we got to the point where we could prove this proposition, this is very useful for proving the proposition. But I only really applied this proposition. But let's give a proof briefly of Hall's theorem. Right? So, right. So one direction is easy. So if G has a perfect matching, this implies that all the neighborhoods must be large, because in particular, if you look at who each vertex got matched to, that gives you distinct elements of the neighborhood. For the other direction, so no perfect matching implies that the matching number of G is less than the size of A. So this is the size of the biggest matching in the graph, right? By Koenig's theorem, this implies that tau of G is less than the size of A because these things are equal. So there's a small vertex cover. So let S be a vertex cover with size smaller than A. Okay, this might have been a bit ambitious to do this in 2 minutes, but let's just, okay. But anyway, maybe 30 more seconds. So this is the set S intersect A. This is the set S intersect B. So if I look at the rest of the vertices here and the rest of the vertices here, there aren't any edges like this. Because by definition of a vertex cover, every edge either has an endpoint here or an endpoint here or both. Right? Every edge has to touch the set S. So there are no edges here. So I let T be the set A minus S. The neighborhood of T is contained in, so there's no edges here, so the neighborhood of this set T must be contained in S intersect B. Okay, and okay, so since we're out of time, I'll just say this set has to be, because A and B have the same size, this set has to be strictly smaller than the size of T, because A and B have the same size, and S is smaller than A. But, okay.